Let's talk a little bit about electron cycling in the mitochondria. I'm very curious in terms of like, what's the mechanism of action here? So is methylene blue, when it's concentrating in the mitochondria, like what is it doing in the process of the ATP when we're looking at the electron transport chain? Like what is it doing there?
Oh, I'm so happy you asked this question. I wasn't sure we were going to go here, but the electron transport chain is this chain of proteins in your mitochondria they're paired, they're all together. There's complex 1, 2, 3, and 4. And the idea is that electrons flow through them, creating this gradient in the mitochondria. The gradient basically pushes what's called a proton against a gradient so that when it comes back down with the gradient, it creates energy. And so actually we eat, especially our carbohydrates and our fat, for these electrons primarily. These electrons, they come into our cells in the part of our mitochondria and they go through this cycle called the Krebs cycle. And you've heard of ketones, of course, right? The ketones do this if you're eating fat. Yep. If carbohydrates is going to be glucose. They go into the carbohydrate. They go into the mitochondria and into the Krebs cycle or the citric acid cycle, and you can actually measure all these things, which is super cool. You can measure all the intermediate steps in the process of creating electrons. And then everybody's heard of these carriers, at least one of them, what's called NAD, and the other one's called FAD. So NADH and FADH are when these carriers pick up these electrons from your food, and they bring these electrons over to your mitochondria. And then these mitochondria, the part of the mitochondria is called the electron transport chain. And then these electrons basically donate to either complex 1 or complex 2, and then they get shuttled across into complex 3 by something called CoQ10. And you have complex 3 and complex 4 that help the whole process through. And at the end, on complex 4, these electrons actually get carried by oxygen. So that's why we actually breathe. Oxygen. We need oxygen because it becomes the final electron acceptor in complex 4. Okay, and then you have those protons that are coming back down the gradient through ATP synthase, which is actually also sometimes called complex 5. But that's this rotor. That's actually a 6,000 RPM motor that actually makes your energy, this ATP. Now, okay, so there's a couple different things here. So what methylene blue does, what it can do, is that oftentimes many of us are walking around with complex 1 or complex 2 dysfunction. Okay, so complex 1 is our NAD carrier, right? So it brings NAD. Well, it takes the electrons from NAD and brings them into the electron transport chain. But many of us, if you've had chronic infections, if you have chronic inflammation, chronic complex medical illness, sympathetic overdrive, so it's like fight or flight all the time and can't get out of
doom. What did you call
it? The sympathetic
spiral
of doom. Yes, yeah, exactly.
Spiral of doom.
Yes, exactly.
Yeah,
so,
yeah.
And then insulin resistance does the same thing. Actually, if you're high blood sugars, you're making too much energy, and actually because you have too much glucose, and then it actually causes a lot of stress, reactive oxygen species stress on complex 1 itself. So what methylene,
which is a natural, sorry to interrupt you, which is a natural function of aging. We also see an increase, a stepwise increase in insulin resistance as we age because of what you're describing.
Right. There's kind of like this chicken before the egg cycle where we become less efficient at using glucose for energy as we get older, more efficient using ketone bodies, actually. Ketones burn cleaner than glucose does typically, especially in the brain and especially as we get older as well. So the key with methylene blue here is that on that electron transport chain, what it can do is it can compensate for any dysfunction that might be happening. So it can actually help recycle that NAD and FAD so it can go back to the citric acid cycle if complex 1 and 2 aren't working very well, and actually can bypass those complexes and donate electrons directly down the chain to like 3 or 4 if needed, and so that you can maintain electron flow even if complex 1 and 2 aren't working very well. So it can basically compensate for the dysfunction in those two complexes, or really any complex on the mitochondria. And the classic example of this is actually something called cyanide poisoning, which I don't recommend anybody get or have, but cyanide actually destroys the 4th complex in the mitochondria. And when that happens, under almost all circumstances, you wouldn't be able to make any energy because everything sort of upstream and downstream will not work. But with methylene blue around, it actually has a capacity to have electron flow through some of those early protein complexes on the mitochondria, and there's electron sink that happens using hydrogen peroxide. So it's a kind of complicated mechanisms, but in essence, what's happening on the energy side is that you can compensate for any of those electron transport chain protein complexes that aren't working well. And a lot of us are walking around with dysfunctional complexes, complex 1 and complex 2 especially. And on the other side of things, when we make that energy, right, we talked about making carbon dioxide, water, reactive oxygen species, which can cause stress on the system if you don't have enough antioxidants around. And what methylene blue can do is work just like an antioxidant. So it can basically mop up free electrons, mop up that oxidative reactive oxygen species, and neutralize it, so you have less stress on the mitochondria. And even at a little bit of a higher dose, methylene blue actually increases your glutathione production as well, which is one of your master antioxidants that helps also do the same kinds of things.
So walk me through how this is different. So I hear, a lot of people in the longevity space like to take metformin because of some of the, and maybe you can explain the difference between what's happening mechanistically at the complex 1 through to 4 with metformin. Because I know that metformin can make people feel tired, but my understanding is that it also upcycles mitochondrial production.
So do you know why? So what metformin does, it actually destroys complex 1 in the mitochondria. It destroys it. And the reason why we think that this is helpful is that the mitochondria are then forced to make new mitochondria. So basically with metformin around, you're forcing your mitochondria to continue to recycle at a much faster rate because that complex 1 is being destroyed. And so that's why people that take metformin actually feel tired, is because that complex 1 isn't working very well. So I'm not a big fan of metformin unless you have diabetes or maybe insulin resistance, and maybe that could be a reason why. But as a longevity drug, I just can't imagine it's a good idea to destroy this complex over time. But I think it's better to build it back up and optimize, your vitamins, minerals, nutrients, cofactors, your lifestyle. But methylene blue can really be helpful here, and I've actually used it in this context, right, where people have been taking this, metformin from like a longevity perspective, and they feel tired all the time. I have them cycle off of it, at least if they want to continue to take it. And then while they're off of it, we give them some methylene blue to help compensate for that dysfunction as well. So it's interesting, right? So proton pump inhibitors are another one was very common. So your Prilosec, omeprazole, Protonix, pantoprazole, these are also destroying complex 2 on the mitochondria. And complex 2 is actually what's actually donating. It's called FAD. So FAD donates electrons from your citric acid cycle into your electron transport chain here as well. So this is another reason why people take these drugs and don't feel very good when they take them. So, and there's other drugs that do this too.
Especially if you're active, right?
Yeah.
Like, especially if you're someone who's already exercising and you're running or you're doing whatever, because like the demand on the mitochondria is just going to be that much higher.
Yeah, so I always say if you really want to take metformin as a longevity drug, do not take it on the days that you exercise, at least not when you exercise hard.